Today, I'm excited to share with you my insights from the study Recent Advances in Modeling Geodetic Time Series and Applications for Earth Science and Environmental Monitoring. This research sits at the exciting crossroads of geology and geodetic engineering, showing us how cutting-edge tools like satellites and radar help decode Earth's dynamic movements. By understanding our planet's geodynamics, we can tackle major environmental challenges like climate change and natural disasters. This study isn't just science, it's a window into how technology makes a real difference in protecting our world. So are you ready and excited to explore this fascinating topic together? But have you ever thought, why do we study geology as geodetic engineering student? Does it connect to each other? What are their similarities and differences? In this video, we will also tackle how geodetic engineering connects to the field of geology. As a second-year geodetic engineering student, geodetic engineering and geology are deeply interconnected fields, as both involve studying the Earth's physical properties and structures to address practical and scientific challenges. Geodetic engineering focuses on measuring and mapping the Earth's surface with precision, utilizing technologies like GPS, satellite imaging, and surveying techniques to create accurate representation of landforms and boundaries. Geology, on the other hand, examines the Earth's composition, processes, and history, providing critical insights into the formation and behavior of the landforms that geodetic engineers map. This relationship is crucial in projects such as infrastructure development, where understanding the geological conditions ensures stability and safety, or in resource exploration, where precise geodetic measurements guide to the discovery of valuable minerals and energy sources. By integrating geodetic engineering spatial accuracy with geology's in-depth analysis, professionals in this field can address complex issues like natural disaster mitigation, land use planning, and environmental sustainability. Did you know that geodesy has a fascinating history? It originated from 1,000 of years ago, with early civilization like the Egyptians using geometry to restore land boundaries after the Nile River floods. Their expertise was crucial in constructing monumental structures such as the Great Pyramid of Giza, precisely aligned with cardinal directions. Fast forward to the 20th century, geodesy underwent a revolution. The development of electronic distance measurement in the 1950s eliminated the need for weeks of manual measurement. By the 1959, the US Navy launched the first satellite navigation system, what we call transit, paving the way for GPS and modern space geodesy. Today, constellations like Galileo and Zhou make precise global positioning accessible to anyone with smartphone. This advancement have expanded geodesy's role from land surveying to monitoring Earth's dynamic processes like tectonic activity and climate impact. This study dives into one of the most cutting-edge areas of geodesy, modeling geodetic time series for environmental monitoring. But what does that mean? Essentially, researchers collect and analyze data over time to track Earth's surface changes, and the primary goal is to extract meaningful patterns, whether it's the slow movement of tectonic plates or sudden shift caused by earthquake, while minimizing noise and errors in the data. Instruments like GNSS, GRACE, and InSAR make these things possible. Wow! And are you excited to explore with me those instruments that make things possible? But before we explore those amazing instruments, can you imagine with me what a satellite looks like? Satellite. A satellite is anything that orbits a planet or a star. Earth is a satellite orbiting the sun, and the moon is a satellite orbiting the Earth. And when you launch a spacecraft into orbit around the Earth, and that's a satellite too. And this kind of satellite can help us learn about our Earth and our universe. Now let's talk about InSAR. InSAR is interferometric synthetic aperture radar. It is a technique for mapping ground deformation using radar images of the Earth's surface that are collected from orbiting satellites. Unlike visible or infrared light, radar waves penetrate most weather clouds and are equally effective in darkness. So with InSAR, it is possible to track ground deformation even in bad weather and even at night. Two big advantages during a volcanic crisis. Two radar images of the same area that were collected at a different time from similar vantage points in space can be compared against each other. and any movement of the ground surface toward or away from the satellites can be measured and portrayed as a picture, not of the surface itself, but of how much the surface moved or deformed during the time between images. Now let's talk about GNSS. What is GNSS? GNSS is a global navigation satellite system. GNSS are invisible pieces of technology that people rely on every day without thinking about it. From communication systems to mobile navigation applications like Google Maps, GNSS affects what we do every day. A global navigation satellite system is a network of satellites broadcasting timing and orbital information used for navigation and positioning measurements. GNSS are more than the satellites orbiting Earth. The multiple groups of satellites known as constellation broadcast signals to master control stations and users of GNSS across the planet. GRACE, on the other hand, or Gravity Recovery and Climate Exchange, is a twin satellite which orbited Earth from 2002 to 2017. It made detailed measurement of Earth's gravity field and improved investigations about Earth's water reservoir over land, ice, and oceans. GRACE measured gravity by relating it to the distance between the two satellites. When there was an increase in gravity ahead of the pair, the front satellite sped up and the distance between the pair increased. When the distance between the pair increased and when the increased gravity was between the pair, their distance decreased. The opposite occurred when there was a decreased gravity ahead of or between the satellite pair. Isn't it amazing how those amazing instruments have their own unique and purpose in our Earth and in our universe? Like GNSS or Global Navigation Satellite System that provides high precision positioning data from over 15,000 permanent stations worldwide detecting millimeter scale movements in our Earth's crust. GRACE, on the other hand, or Gravity Recovery and Climate Exchange, measures changes in Earth's gravity field, revealing water mass shift, melting glaciers, and groundwater depletion. Lastly is InSAR that uses satellite radar to detect ground deformation even in remote or inaccessible areas, making it a game changer for landslide and volcanic monitoring. The study highlights how these tools are combined to model Earth's behavior and address critical environmental challenges. So now let's talk about the real-world applications of geodetic time series, from crustal deformation monitoring to natural hazard detection and to climate monitoring. In crustal deformation monitoring, geodetic tools are invaluable for understanding how tectonic plates interact. GNSS has detected pre-seismic deformation in areas like the San Andreas Fault, providing early warning of potential earthquakes. Moreover, GNSS and InSAR have revealed the gradual uplift of land in regions previously burdened by glaciers, which is a process known as a glacial rebound. Natural hazard detection, on the other hand, is one remarkable application is in landslide monitoring. For instance, in the Baijibao region of China, GNSS and InSAR combined with AI algorithm successfully forecasted landslide displacement, helping to protect vulnerable communities. Additionally, these tools are used to study volcanic activity by tracking the inflation or deflation of magma chambers beneath the surface. Lastly is the climate monitoring. Climate change impacts such as sea level rise are meticulously tracked using GRACE and GNSS. GRACE has revealed an 8 cm global sea level rise since 1992, primarily due to the melting ice sheets, and this data empowers coastal cities to design resilient strategies against flooding and storm surge. Similarly, GRACE data has been instrumental in tracking groundwater depletion in drought-stricken regions like California, providing critical insights for sustainable water management. And as you can see from the comparative graphs showing noisy versus corrected geodetic data, red means the noisy data, which the observed signal affected by the random errors and irrelevant fluctuations. Blue is the corrected data, where the filtered signals are applying advanced noise modeling techniques to isolate meaningful patterns, and green data, which is the true signal, which is the actual geodetic signal or the ground truth that is used as a reference. In the age of technological breakthroughs, geodesy stands as a testament to how science can bridge history, innovation, and real-world applications. From the ancient Egyptians aligning their monuments to the millimeter-scale precision of GNSS, GRACE, and InSAR today, we've come a long way in understanding our Earth's dynamic processes. This journey isn't just about science, it's about safeguarding our future, our universe. By unraveling tectonic shifts, monitoring natural hazards, and tracking climate change impacts, geodesy empowers to make informed decisions for a more suitable and resilient world. So let's embrace the power of geodetic engineering and geology, not just as a tool of the trade, but as keys to unlocking a deeper connections with the planet that we call home. With the knowledge, innovation, and collaboration, there's no challenge too great. Thank you for joining me in this exploration, and together we've got tools to make a difference. And you have the power to make the difference.